Hello everyone, I'm Diego Carraro. I'm a PhD student at Insight Center for Data Analytics in the University College Cork in Ireland. In this video, I will present the paper I have written in collaboration with my supervisor, Dr. Derek Bridge. And the title of the paper is Debiased Offline Evaluation of Recommender Systems, a Weighted Sampling Approach. So, classical offline evaluation of recommender system is done using an observed dataset. And this observed dataset records interactions that occur between users and items during a given period of time in the operation of the recommender system. And those interactions can be clicks, purchases, ratings, or whatever. However, this dataset is often biased due to many factors, and those factors are known as confounders. Examples of such confounders are the user freedom to rate items or the user interface of a recommender system, because differences in the ways that items are exposed to users, for example the position on the screen of those items, clearly influence the likelihood of a user interacting with those items. Also, the recommender system algorithm is a confounder, because we know that users are typically more likely to interact with items recommended rather than with other items. Also, item popularity is a confounder. The distinction between biased and unbiased data is based on the missing data analysis theory, where the missing data mechanism describes the process that generates the observation pattern in the data. In other words, the missing data mechanism describes how data is collected or generated. So, biased data is missing not at random because missing interactions depend on some confounders in the data, while unbiased data is missing at random because missing interactions do not depend on any confounder in the data, whether it is observed or not. So, in the following, I will use biased and MNAR interchangeably, and the same for unbiased and MAR. Classical offline evaluation has the incorrect assumption that data is MAR instead of MNAR. But using MNAR data as if it were MAR could lead to biased estimates of a recommender's performance, thus resulting in a biased evaluation. But design an unbiased offline evaluation is possible, and the most straightforward solution is to collect and employ an unbiased dataset. But for reasons I won't explain for time limits, this approach is easier in some domains, but either impractical or too expensive in many other domains. Another solution is to design unbiased estimators that compensate for the bias in the MNAR data, but they might not be general enough to overcome all sources of bias, or their biasness might be proven only if data satisfies some specific conditions. In our work, we focus on a third approach, which consists in intervening on MNAR data before using it for the evaluation. The goal of the intervention approach is to perform a debiasing intervention on MNAR data by means of a given sampling strategy S. So, we denote the observed user item interactions in a dataset D by using O superscript D. Using those notations, the output of the intervention is a subset OS of OMNAR with the goal that OS has unbiased-like properties. We also denote by italic and bold O the binary random variable over the set of user item pairs in O. O equal to 1 if the user item interaction is observed, and O equals to 0 otherwise. We will use this notation in the following slides. Another notation that we need is italic and bold S, which is the binary random variable that guides the sampling. S equal to 1 when a particular user item pair is sampled, 0 otherwise. And the figure visually describes the idea of the intervention, where practically we need to design the strategy S, so the probability distribution that we will use to perform the sampling. I will now introduce WTD, which is our intervention approach to unbiased evaluation. In input we have OMNAR, which is the biased dataset that we want to debias. For the moment, we also assume the availability of a small MAR-like dataset or MAR. The idea of WTD is to make the posterior probability of each user item pair in the sampled OS approximately the same as the posterior distribution observed for the corresponding user item pair in OMAR. And this concept is expressed by Formula 1. And we do it by adjusting the MNAR posterior, making use of specific user item weights. So Formula 2 says that we want to make MNAR posteriors equal to MAR ones. Now we can rewrite the right-hand side of Formula 2 in two ways, leading to formulas 4 and 5. Formula 4 says that a specific weighted MNAR posterior can be written as the product of the corresponding user and item MAR posteriors, which are independent with respect to each other. And we can write that because MAR data is uniformly distributed over users and items. Similarly to Formula 4, Formula 5 uses an independence property, this time the one of the weighted MNAR posteriors. Even if this theoretical independence is not verified by MNAR data in practice, we will show that leveraging this assumption shows empirical good results. Formula 6 says that we want to weight a specific MNAR user posterior to be the same as the corresponding user MAR posterior, and similarly for the items in Formula 7. Thanks to Formula 6 and 7, we can define and calculate user-specific weights and item-specific weights instead of weights that are user-item specific. How? Well, let's consider a specific user U. We express her weighted MNAR posterior by the product of a specific user weight WU and use original MNAR posterior that is calculated from the MNAR data. This choice of modeling the weighted MNAR posterior of user U is arbitrary. Indeed, we could have used other ways. We plug this definition into Formula 6 and we obtain Formula 8. We use the same approach for a specific item and we get Formula 9. Now, we just have to reverse Formula 8 and 9 to get the formulas of how to calculate the user-specific and the item-specific weights. To some extent, we can think of the calculated weights as quantities that measure the divergence between the MNAR distributions of the sampling space and the target MAR distributions. We directly use weights to model the sampling distribution of the sampling strategy S, which will perform the debiasing sampling. The role of a specific weight is to adjust the corresponding MNAR distribution then. Practically, during the sampling, the effect of the weights is to increase or decrease the probability that a particular user item pair is sampled, depending on how divergent are the user and item posterior probabilities in the MNAR sampling space with respect to MAR distributions. But instead of the sampling distribution that you see above, for the strategy S, we used a different version colored in green on the bottom of the slide. And this is because it raises the importance of the item weight relative to the user weight. This version in green was designed after some preliminary experiments which tell us that items weights have a bigger impact with respect to user weights. In order to calculate the weights in practice, we need the availability of some MAR-like data. So, what if we don't have any MAR data? Because I recall you that we said that it's not always possible or it's not always easy to get such kind of data. Well, we designed WTDH because we can use hypothesized posterior probability distributions for MAR instead of the ones calculated using real MAR data. And this is possible because MAR data is typically uniformly distributed over users and items. This is the methodology we use for our experiments. It looks complicated, but I will try to make it simple. Of course, more details are included in the paper. The objective of the experiments is to assess if and to what extent the intervention approach, and in particular our proposed WTD, are successful in reducing the bias in the evaluation. So, we take a dataset which has both MAR and MNAR data portions. Once we have it, we take the MNAR portion and we randomly split it into two, a training set OTR and a test set OHE, as we would normally do in a classical evaluation. We use the training set to learn a recommender model because our goal is to debias the evaluation only, not the training. But differently from the classical evaluation, we take the test set OHE and we perform an intervention to debias such test set, resulting in an intervened test set OS. We now take the MAR data and we randomly split it into two. The MAR held out OW is used to calculate weights for our approach WTD. OGT is instead used as an unbiased ground truth test set used to assess real unbiased performances of a recommender. In the experiments, we compare 5 sampling strategies that sample from the held out test set OHE. Each strategy produces a different intervening test set. Full samples the entire OHE so that no intervention is performed. Reg corresponds to the classical way of generating a test set. Indeed, it randomly samples from OHE. Skew, which sample user-item interactions in inverse proportion to item popularity, thus producing test data with reduced popularity bias. And finally, WTD and WTDH, our two approaches explained in the previous slides. Again, we highlight that each of those sampling strategies produces a different intervening test set. In total, we have 5 different intervening test sets. We employ 2 datasets. They both have a missing not at random and a missing at random portions, which is what we need to run our experiments. Code Shopping is a dataset in the clothing domain, and WebScope in the music domain. We train 5 recommender models, all of them producing a ranked list of recommended items. AVG rating ranks items in descending order of their mean rating in the training set OTR. PostPop ranks items in descending order of the number of positive ratings in the training set OTR. UBKNN is a user-based nearest neighbors algorithm. IBKNN is an item-based nearest neighbor algorithm. And finally, MF is a matrix factorization algorithm. For each recommender, we calculate recall at 10 on the ground truth test set OGT. We also calculate recall at 10 on the 5 intervening test set. We report the percentage difference of performances on the intervening test sets with respect to this OGT. In general, we want the performance of a recommender on an intervening test set to be close to its performance on this unbiased test set OGT. The best intervention strategy is the one that produces the lowest percentage differences. This slide reports results on the Code Shopping dataset. They show that all intervening test sets overestimate ground truth performances for all recommenders, with just one exception: popular positivity on WTDH. In general, our new approaches are superior in approximating ground truth performances. WTD is very close for non-personalized recommenders performances, like PostPop and AVG rating, while WTDH is the best for the personalized ones. Although both of them outperform all the other strategies, WTDH would probably be the best choice due to its balance. Indeed, its percentage differences are not more than around 50% from the ground truth for all the recommenders except MF, which anyway has the best approximation on WTDH among all the strategies. This slide reports results on the WebScope dataset, and the same methodology used for code shopping applies. But result shows something slightly different now. First of all, for the AVG rating recommender, ground truth performances are underestimated by all strategies. For this recommender, skew, WTD and WTDH are equally good, but superior for full and reg anyway. We then find skew superior to WTD and WTDH for the post-pop recommender. But WTD and WTDH are better for the personalized recommenders. This fact is expected to some extent because skew is a popularity bias specific intervention strategy. Comparing only WTD and WTDH, we find that both are close to each other, but we also find that the former more closely approximates the ground truth for post-pop, UBKNN and IBKNN, while the latter does it for MF and AVG rating. In conclusion, we have presented WTD, an intervention approach that effectively mitigates the bias in the test set. WTD enjoys low overheads. Indeed, there is no need for learning, because weights are calculated at no cost. WTD works with MAR data, but WTDH works without MAR data. And finally, the intervention results in smaller test sets. WTD also has high generality because it works for both explicit and implicit datasets and can be used to debias training sets as well as test sets. Finally, it works with existing training algorithms and evaluation metrics without changing them. The video presentation is over. Thanks for your attention, and if you have any question, you can email me or Derek.